terms we are going to, and they're important terms. They're terms that we're going to need to use. So I want to take a deep breath. You need to get a bunch of paper and a pencil handy, and be ready to pause the video as you watch it, and do your best to answer some open-ended questions I'm gonna give you. Okay, it's gonna be probably a little uncomfortable. You need to be ready to try some difficult things. Okay. So first of all, I'm going to talk about limiting reagent or limiting reactant. Tro uses the term reactant a lot. He also uses reagent. I use those. Okay, so let me just remind you, these over here are reactants. These over here are what? If I was going to use this language for these compounds, what would I call these? I would call these products, right? Okay, so in the nice tight little stories we've been describing here with carbon dioxide and methane, for example, or carbon dioxide and methane and oxygen, we don't have a limiter, right? There's one carbon atom, 4 hydrogen atoms, 4 hydrogen atoms, 4 oxygen atoms, 4, right? Everything comes out perfectly. But suppose we did this, we burned methane in the open air. Well, if we burned it in the open air, we don't have 2 oxygen molecules. We have tons of these things, right? They're everywhere. Just draw them, right? They're all over the place. We've got a bunch. So how many, if you let each one of these things represent an oxygen atom that I've drawn, or oxygen molecules, how many oxygen molecules do you see? Right, these are all oxygen molecules. How many oxygen molecules do you see on your screen? Let's see. 1, 2, 3, 4, 5, 6, right? So you might have 6 oxygen molecules. Well, in that case, how much carbon dioxide can we make if you're doing this in open air? How much carbon dioxide can you make? How much? If you burn 1 mole of methane in the open air, you can still only get 1, right? Because you only have 1 carbon atom. So in this case, we would say that methane is the limiter, or the limiting reagent. Okay, or reactant. All right? And what would you call oxygen? Oxygen then is going to be the excess reagent. All right? And you wouldn't call these guys anything. They're products. Okay? So we have introduced here 2 terms, and we're going to come back to these terms over and over again. Limiting reagent. My watch keeps going off. Can someone go get my phone, please? Limiting reagent, that's one term, and the other one is the excess reagent, okay? And if you've got this in open air, then it's likely your oxygen is going to be your excess reagent, and the thing that you're burning is going to be your limiting reagent. All right, so let's look at those again. All right, limiting reactant or reagent. This is defined in your book on page 132, okay? Tro 132. Tro, thank you, 132. Okay, the reagent is completely consumed. A limiting reagent is the reagent that's completely consumed in a chemical reaction, and it limits the amount of the product, okay? Just like we described with methane air. The excess reactant, or what, right? Fill in the blank. The excess reactant or reagent is the other one. That's the stuff that we have left over, right? So if you burn something in air, you don't expect that the air is going to be completely gone when you're done. You have an excess reagent in its air, right? Any reactant is defined on page 132 of Tro. Any reactant that occurs in a quantity greater than what is required. All right? Now, there's a couple more terms that are defined on page 132. And we need to look at those. So they are theoretical yield, So a theoretical yield is the amount of product that can be made. Let me emphasize that here. Theoretically, this much can be made in a chemical reaction based upon how much we have available. Okay? The actual yield is the amount that we do make. All right? And then the percent yield is just what you might think. It's the actual over theoretical. And usually we say actual because we want percent, not a fraction. We'll say actual over theoretical. And we'll say times 100% because we want to change the form of the number to a percent. Okay, so the percent yield is actually, it's the fraction of what you've got over what you could have gotten if everything had worked out perfectly with no losses. All right, so these are our terms. We're going to practice those a good bit. Now with this next slide, I want you to take a blank sheet of paper and think about our pizza question. All right, and I want you to look at your textbook at the definitions of theoretical yield and actual yield, and I want you to make up a question. You need to make up your own question where this graphic would help you solve the problem. Okay, you know what I'm saying? Pause it, and I want you to try, even if you don't know what I'm saying. I want you to try to make up a story problem where this graphic is relevant. Pause it now. Okay. All right. So that's an open-ended question. There's actually many story problems where you might, where this might have been relevant. But I'm going to go back to my definition on the previous page, or on page 132 still, previous slide. It says percent yield. Here's the one I'm going to make up. Okay. Percent yield is defined as the actual over theoretical. I'm going to pull out the definition times 100%, which I have right here, right? So I'm going to say, all right, here's my question. I'm going to say, suppose Jeff has enough materials to make 3 pizzas. He ruins some in process. I won't even say how he ruins it, okay? He makes 2 edible pizzas. What is his percent yield? Okay, so this is a little bit absurd because we never talk about a percent yield when we're talking about 2 and 3 pizzas, okay? But I recommend that you do this with these terms. You need to make up your own problems. You need to make up your own problems. It's a totally different mindset than when you're simply taking the problems that I give you. So it's extremely uncomfortable to do that. I remember when my professor in the fall of 1994, Leon Mandel, said to a big auditorium class of 250 students, I was sitting in the front row. He said, "You got to make up your own problems." And I remember thinking, there's no way I can do that. But I will tell you folks, having tried it then, and eventually got the hang of it, I will tell you it is the key to you mastering this material with as little effort as possible. It's the most efficient way to do it. Okay. So I think I might have another slide here for you, like that. I've forgotten. Yeah. Here's another one. Okay, do it again. So I want you to pause the video, and I want you to make up a problem where this is a graphic that is relevant. Okay, I'm going to assume you paused the video. I'm going to make up one also, and I'm going to say, suppose Randy has 5 moles of methane. How much carbon dioxide can he make? Now again, I will admit again that this is a bit absurd, right? Why would Randy have 5 moles of methane? Why would Randy have 5 moles of methane? What kind of a scenario would that be, right? So I'm going for the most simple possible question that I could make up with something like this. All right, and you should do it. It's going to help you appreciate what's going on. So what are we doing here? What is this process? This is simply a conversion. It's actually a molar conversion. And this is a molar ratio. Okay? You need to get your eyes used to looking at these things. So hopefully in these upcoming videos I'll pull out some more of these graphics and ask you to do the same thing. You must do this. It will help you so much. Alright, I think it's time to do a problem. Let's go to the first limiting reactant and theoretical yield problem. Alright, so ammonia can be synthesized according to this reaction. Whoa, 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 whoa. That's not ammonia. Not sure. I got this from the text. So let me say what reaction should have been here. Can be synthesized. So for making ammonia, it comes from that, and I happen to know this reaction. It's from nitrogen and I'm going to do this again. This reaction is nitrogen gas plus hydrogen gas gives ammonia. Let's balance this. There must be 2 of these. There must be 3 of these. Not the right reaction. Starting with 86.3, I'm going to look at the book and see if it's the same problem there. No, the correct graphic is in your book, but not here. So starting with 86.3. Oh, whoa. Wait a second. You know what? This is the Haber process. This is not the right reaction because we're not starting with NO. Let me get rid of that. Put the right reaction. I'm going to look in my book and see the right reaction. This is a reaction with which I'm not familiar. This is with nitric oxide, or nitrogen monoxide, if we're going to name that, plus what? Hydrogen gas. You would never know this, okay, folks? I'm looking this up in the book. Gives 2 moles of ammonia plus 2 moles of water. This is not balanced. I think there's a 5 in here and a 2 moles. Okay, so this is the reactant we're supposed to be given here in this slide. All right, so starting with 86.3 grams. All right, what a mess. Let me write it down here. NO plus 5H2 produces 2 moles of ammonia plus 2 moles of water. Pardon the background noise. I'm working in sort of a common work area, and I'm afraid I can't do anything about it. So, all right. So starting with 86.3 grams of nitric oxide. So remember now, I'm going to use this as a table. This is grams. 86.3. I always need to use a molar ratio. You've seen me do this before. So I'm going to set those up like that. And 25.6 grams of hydrogen. 25.6 grams of hydrogen. All right? The formula weight of hydrogen is 2.016. And nitric oxide is 1 times nitrogen plus 1 times oxygen, which is 14.01 plus 16.00 according to the periodic table on the inside of my front book. So this is going to be, looks like it's 30.01. All right, so the moles. I'm not going to say much about this. I'm going to try to keep my mouth shut while I'm doing this. 36.3 divided by 30.01 is equal to 2.8757. Put a little extra digit in there for now. And 25.6 divided by 2.016 is equal to 12.698. Okay? So the real question is, so find the theoretical yield of ammonia in grams. All right, the question is, if I have this many moles of nitric oxide, how much ammonia can I make? The next question is, if I've got this many moles of hydrogen, how much nitric oxide can I make? All right, so we're going to do this. First of all, I'm going to say suppose nitric oxide. And that is 2.8757 moles. I'm going to call this A, B, C, and D. Moles of A, just to keep things simple. Moles of A. And I'm looking for what's my theoretical yield of ammonia, which is here. How many moles of ammonia can I get? Now suppose I consider my hydrogen. If I have 12.698 moles of, and I'm using B up here for that one, right? B, moles of B is equal to moles of C. Can you see what I've got my molar ratio here? Moles of C. Moles of C. I'm going to come down here, go to pen color, black. This is my molar ratio right here, right? It's a very simple conversion. So what numbers go here? Looks like I've got 2 moles of C for every 2 moles of A. Right, and for this one, it looks like I've got 2 moles of C for every 5 moles of A. All right. So it looks like these are going to cross off, these are going to cross off, and I'm going to be left with 2.876 moles of C. I don't want to leave myself enough room there. And this one I cannot do in my head. 12.698 times 2 divided by 5 is equal to 5.079. 5.079. So which of these is less? This one's less, right? It looks like this is going to be my limiting reagent. All right, so if that's my limiting reagent, then I'm going to say, well, that must be how much I make then. I must run out of nitric oxide before I run out of hydrogen. I must have extra hydrogen. So it's 2.8757 moles of ammonia. The formula weight of ammonia is 1 times ammonia, or times nitrogen, plus 3 times oxygen, or hydrogen, 1.008, 14.01, clear, 1.008 times 3 plus 14.01 is 17.034. And so how many grams, it's because it's this, what's the theoretical yield in grams. So how many grams of ammonia am I going to get? 17.034 times 2.8757 is equal to 48.98 grams of ammonia, right? That's what I'm looking for, grams of ammonia. Now, let's go back through here and see. I've got 3 sig figs here, and I got that from our periodic table, so it's 4. I must have 3 here. I wrote 5 out, but there's only 3 that I can use. Therefore, this must have 3. This has got 5 because I got it from my periodic table, so this must only have 3, okay? So what's that going to take me to? 49.0 grams. All right, 49.0 grams of ammonia. And that is my answer. Okay, so again in review, I considered, suppose I had an unlimited amount of hydrogen, how much could I make from nitric oxide? And then I suppose the opposite. Suppose I have an unlimited amount of NO, nitric oxide, how much could I make if H2 were my limiter, right? And I saw, aha, I run out of the one before I do the other. It's always the smaller one which is going to be your limiting reagent. Okay? So this is described very nicely on page 134. What I've said here just now, page 134 intro. You may want to go look at that. I was a little bit short in my explanation there with the purpose of keeping things simple. Let's do it again. One more example and we'll be done. So titanium metal, I'm going to go back to my other color now, P. Let's go back to red. Titanium metal, and I'm going to use this as my column here, okay? When I'm going to call this A, this B, this C. This is going to be confusing because that's already C, isn't it? I'm going to do that. You know what I'm going to do? I'm going to call this A. Since it's already C, I'm going to call that C. We'll call that B and this D. All right, just for shorthand. When 28.6 kilograms of carbon reacts with this much. All right, so I'm going to go with, here's my table. This is my column heading. I'm going to look right past this text right here. And I'm going to say in kilograms, then my mass in grams. We're always going to have to go through a molar ratio. So I'm going to do my formula weight. Grams per mole. Okay, and moles. So when 88.2 kilograms of titanium, looks like it's titanium 4 oxide, right? Because I'm using my nomenclature there. Titanium's a transition metal. So we're going to say titanium 4 oxide. Where am I here? 88.2 kilograms. So this is 88, watch this, 0.2 kilograms, okay? Formula weight, we'll look that up in a minute, is reacted with 28.6 kilograms of carbon. Here's my column for that. 28.6 grams, or rather kilograms, 28.6 times 10 to the 3 grams. Okay, and carbon, I know carbon's 12.01. Okay, according to the periodic table, it's 12.01. I'm verifying that. I'm going to come over here and do my titanium oxide. It's 1 times titanium plus 2 times oxygen. And oxygen is 16.00. I remember that one. Looking up titanium now, it's 47.87. 47.87 plus 32 is 79.87, okay? 79.87. So how many moles does that give us? Just a moment here. 88.2 times 10 to the 3 divided by 79.87. Oops, got something wrong here in my calculator. Let me do it again. 88.2 times 10 to the 3 divided by 79.87 equals 1104.3. 1104.3, okay? And then carbon's 28.6 times 10 to the 3 divided by 12.01 equals 2381.3, okay? So then the question is, which of these is the limiting reagent? You see what I'm doing here? Can you see that this is my table, my column for A, this is my column for C? So the question is, determine the limiting reactant. We weren't asked, it does say this much of titanium is produced. Okay. So I do need that here, okay? My column's kind of running out here. Looks like it's 42.8 kilograms, and so it's going to be 42.8 kilo, right? All right, so that's much is produced. All right, so the first thing we're going to do is find our limiting reagents. So we're going to say if I've got a certain number of moles of A, and I'm using B for titanium, right? How many moles of B can I make? And then I'm going to consider, that's in scenario number 1. In scenario number 2, I'm going to say, suppose I've got a certain number of moles of C, because this is my C, right? How many moles of B can I make? And whichever is less, that's the limiting reagent. So for A, it looks like I've got to cross off moles of A, moles of B. Here's my molar ratio. Moles of B, and what's going to go right here? Moles of C. Okay, so let's change our color now. All right, and what number goes right here? Just a minute here, 1104.3. And what number goes right here? It looks like it's 1 to 1. Okay, what number goes here? How many moles of C am I starting out with? You really should pause this video and finish out this problem if you can. You should try to do that. And how many moles of B for every mole of C? It looks like I've got 1 mole of B for every 2 moles of C. Okay, so this is going to get divided in 2. 2 equals. So this goes to 1190.7. You agree these moles cross off and I'm left with moles of B, right? These moles of A cross off and I'm left with moles of B, right? So this is, it's 1 to 1. This is 1104.3. So which is the limiting reagent? Which is it? You need to make a guess here. I beg of you, make a guess. Okay, so this is the limiting reagent because it's the less, right? So how much theoretically can I make? I theoretically can. Oops, this was real up here. This is how much I really made. I should have put theoretical, okay? Real or actual. Okay, right? That's what is produced. Okay? So how much can I make? I can make 1104.3 moles of titanium. Okay? So how many grams of titanium does that give me? Right? Titanium is here. I just looked up my periodic table a minute ago. 47.87. This is going to give me what? 1104.3 times 47.87 is equal to 52863 grams, okay? Which is equal to 52.863 kilograms, right? So this is my theoretical. This is, let me go back to a different color, okay? Let me go back to red. Watch this now, how much I could have made if I used all of my limiting reagent and lost none. That's what theoretical is. That's how much. That's what it is. It's how much you could make if you use all of your limiting reagent. You lose none. You have no loss in the process. Okay, but apparently I do have some loss in the process because I could have made. That's my theoretical. Here's my actual in kilograms, right? So what's my percent yield? My percent yield is 42.8 over 52.863 times 100, right? So let's do that. Times 42.8 equals 0.8096. Wait, times 100 equals 80.96. All right, looking in the book real quickly here. If there's a mistake here, I want to see it before I close this video out. That's it. 80.96. Okay. 80.96%. There's 3 sig figs here. There's 5 sig figs here. And so this has to go to 3. This goes then to 81.0%. Okay, Tro says it's 80.9, so we've got a rounding issue somewhere. There is the answer. Okay, hope that's helpful. There's a lot here. Just let me end this presentation by going back to these terms here. Limiting reagent is the reagent that is completely consumed in a chemical reaction, and it limits the amount of product. The excess reagent is the other thing. That's the stuff we have left over. Theoretical yields the amount of a product that can be made in a chemical reaction based upon the amount of limiting reagent. That's how much could be made in a perfect world. Okay, an actual yield is the amount that we get. Usually the problem will say X grams is produced. You're supposed to figure out theoretical, and they give you how much is produced. That's how much is actually produced, and then percent is actual divided by theoretical. In other words, that's really a fraction of how well you think you did, or not well how you think you did, how well you actually did, right? So if you get 100% yield, that means that you did a good job. And anything less than that is just due to experimental challenges and loss in process. Okay.